Hi class, I promised I would go through a sample calculation of the microproject exercise to generate a random planet using dice. So in this exercise we're utilizing some of the mathematical framework that we've developed over the term. We haven't used it a lot, but it's kind of straightforward algebra, so it's stuff that I think you should be able to manipulate and do on your calculators. But I wanted to do an example for you to kind of help you flex those skills if you haven't used them in a while. So on the assignment sheet, the microtheme exercise or microproject exercise, I gave you a long set of instructions, and in particular there's a table, and this table has all of the data on it that you need about the properties of your star. So in particular, based on your last name, you pick a particular spectral type, and then the properties of the star are listed in the columns. And then, as we noted in the instructions, you'll notice that the columns are given in units of the sun's value. Okay, so it's L times L sun, R times R sun, M times M sun to get the correct value. So those values for the sun are given right there, and to get the value for your star, you take the value that's there in a column. Say you were trying to calculate the radius, and I was a type 06 star. Then that's 12.2 times the radius of the sun. So I take 12.2 and I multiply it by 6.96 times 10 to the 8 meters, and I get the radius of the sun. Okay, so since I don't want to do an example that's actually on the sheet, I picked a star that is not on the sheet. So I'm going to deal with a star, a real star called 82 Eridani. 82 Eridani is in the constellation Eridanus. It has a name, 82, so it's actually visible to the naked eye. Eridanus is the Great Sky River. It kind of comes off the knee of Orion. Okay, and if I look up the properties of 82 Eridani, and I'll try and write a little bit bigger there because on the video it looks a little bit smaller, the spectral type is G6V. Okay, now that's not in your table, but that's okay because I want to do an example that's not one any of you are doing. If I look up the exact mass of 82 Eridani, it's 0.7 times the mass of the sun. So if I multiply that by the mass of the sun, which is 1.98 times 10 to the 30 kilograms, then I get the true mass, or the mass for 82 Eridani that I care about, which is 1.386 times 10 to the 30 kilograms, or that's equivalent to writing 1.386 E 30 kilograms, which is how it appears on your calculator. Okay? Okay, so if I look up the radius of 82 Eridani, it is given as 0.92 times the radius of the sun. Okay, that little circle with a dot is a symbol that astronomers often use to mean solar value or value of the sun. So I'm going to multiply that times the radius of the sun. So the radius of the sun is 6.96 times 10 to the 8 meters. And if I multiply that all out, I get 6.403 times 10 to the 8 meters is the radius of my star. Okay, and then lastly, I need to know the luminosity of the star. So the luminosity of the star is going to go into the calculation of our habitable zone. So if I look up the luminosity of 82 Eridani, so the luminosity is 0.74 times the solar value. So if I multiply that by the luminosity of the sun, which is 3.83 times 10 to the 26 watts, and I work that all out for 82 Eridani, the luminosity L star is 2.83 times 10 to the 26 watts. Okay? So those are all my values for my star, and we will use them as part of our calculation here on the as we go through the exercise. Okay? So I'm going to set those aside, and I will keep them handy so that I can look at them. Now, the next thing we were going to do, or that you're asked to do, is to calculate the location of the habitable zone. And the habitable zone depends on two things. It depends on the properties of the star, namely the luminosity of the star, and I've just calculated the luminosity of my star right here. This quantity here that I calculated is L star, okay? So it depends on the luminosity of the star, but then it depends on how far away from the star you are, okay? So for any given planet, it'll have some distance d, okay? But there's some distance, which we call d inner, where water boils away, where it can't exist on the surface of the planet. And so at that point is where the amount of energy that the planet receives from the star, K star, has this value 1925 watts per meter squared. Okay? Similarly, if I imagine a planet a bit farther away, it has its own distance. Let me call that d outer. Okay, so that planet's orbital radius is where water freezes. And that happens when K star has a value of 470 watts per meter squared. Okay? And so the point here has been that all the region between these two, for the entire orbit that goes around the star, is what we call the habitable zone. And if you go look at equation in lecture 17, okay, if I tell you L star and I tell you a value of K star, you can use it to calculate the distance d. And that distance d is given as the square root of the value of L star, which you know, divided by 4, which you know, pi, which you know, or you can look up, okay, times the value of, pi squared. Pi squared? Nope, just pi. Okay? Times the value of K star that you happen to be interested in. So if I want to calculate the location of the inner habitable zone, I put in this value of K star and I put in the value of L star, and I can calculate d inner. If I want to calculate the location of the outer part of the habitable zone, I put in this value of K star, I put in the same value of L star, and that gives me d outer. Okay? So it's just an exercise in plugging in numbers that you've already calculated. So you can do those on your calculator. I won't do that here in front of you. But for my star, for 82 Eridani, okay, I can use these values of K star, and I can use this value of L star, and I will get that d inner is equal to 1.08 times 10 to the 11 meters. And since I don't like writing out exponents all the time, I will convert that into astronomical units. That is 0.72 astronomical units. So that's a bit closer to 82 Eridani than the Sun is to Earth. Similarly, if I calculate d outer, okay, so I use this value of L star, I use the outer value of K star, And if I calculate d outer in this case, I get 2.19 times 10 to the 11 meters. And again, if I compute that to astronomical units, that is 1.46 astronomical units. And that's a bit closer to the sun than Mars is to our own sun. Okay? So one of the things that the exercise asks you to do is to calculate a set of spacings that we can use to randomly generate a position for the planet. That is called delta D. So that is just D outer minus D inner divided by 5. Okay, and if I do that, I get 0.148 astronomical units. Okay, which I could also convert to meters. And in fact, for all of the calculations that use formulas, you should always use the values in meters. Okay, the values in astronomical units are there for convenience of discussion. Okay, so now we get to the random part. So at this point, we want to generate a random position for our planet based on this location, this spacing of orbits, and the location of the habitable zone. And so the way the instructions tell you to do that is we're going to roll some dice. Okay, so I had my dice here at the beginning, which you can saw. So for the location of the planet, it's D inner. We want to put our planet in the habitable zone. So it's going to be D inner plus, sorry I wrote an equal sign there. Not doing so well on the video today, am I, class? Plus 1d6. That's my random roll. Okay. Minus 1. Times delta D. So if I roll, I got a 3 there. Okay, so 3 minus 1 is 2. So location of my planet is D inner plus 2 times delta D. So that is 0.72 astronomical units plus 2 times 0.148 astronomical units. And if I calculate that on my calculator, so since I rolled the dice live in front of you, I didn't do that calculation. So that is 0.72, 148. So this is 1.01 astronomical units. So this is about the distance of the Earth from the Sun. Okay, and if I convert that into meters, because we certainly need to have things in metric units when we do the calculations, if I convert that into meters, I get that that is 1.52 times 10 to the 11 meters. Okay? So this is the distance of my planet from the star. Okay? So that's how you go through that calculation. That shows how you do an example calculation with the dice, and it shows you in particular how you utilize one of the formulas that we had in class in lecture 17. Okay, now I'm not going to go through the whole calculation again, but let me do one more clarifying statement here, and that has to do with the surface gravity of the planet. Okay, so you'll remember that when we talked about surface gravity, we were talking about the gravitational force, and it depends on the properties of the planet. So the planet has two fundamental properties. It has its mass, which we'll call big M, and it has its radius, r. And the surface gravity is what do you feel when you're standing on the surface of the planet. Now you'll remember that we said the universal law of gravitation can be written as G, Newton's constant, times the mass of the planet, times your mass divided by the radius of the planet squared. Okay, and something we didn't do the first time we learned about that is we didn't write it out in a second step, but I can write it out in the following way. I can put some parentheses here. G times the mass of the planet divided by the radius of the planet squared times your mass. And the reason I do that is because all of the properties right here in the parentheses have to do with the properties of the planet. And so this quantity in parentheses is what we call the surface gravity. So I could write the universal law of gravitation this way or this way, where I've made the identity that the surface gravity is G times the mass of the planet divided by the radius of the planet squared. Okay, and if you look in the lecture notes for lecture 17, which is the place where you'll find the description of the inner and habitable zone and outer habitable zone radius calculations, you'll see that we wrote the surface gravity in this form there. Okay? Okay, so I hope that provides a little bit of guidance. I've been answering a few emails. That kind of covers the most common ones that I get. If you do have any more questions before the end of the week, please do let me know. And I hope you're all safe and well, and we'll talk to you again soon. Take care.